Hello grade 12s, welcome to yet another video, and today we're going to be looking at the physical science paper 2 written as a supplementary exams during this May-June exams. Alright, we'll be highlighting a little bit of some mental preparation for each section as we go through it, so that it can give you a bit of an idea as to how you can get yourself in a calm state approaching these papers. Otherwise, if you wrote this paper, this may serve as some sort of a memo, but if you haven't written this paper, it will serve as a preparation for your trial exams because it is at that level, as well as your finals. Alright, so let's get to the work and start running. Of course, instructions. What you want these operational instructions. For example, you know that if you're doing a calculation, you're expected to show formulae and substitutions. The rounding off, this time it's minimum of 2 decimal places. So that means 2 or more, but no less than 2. And then of course, for motivations or some discussions, keep them brief and to the point. And obviously, when you run into a corner out of commission, there is help for you in the data sheets for any formula that you may have forgotten. Okay, let's get to question 1. So it's multiple choice. So we are told here, various options are provided as possible answers to the following questions. Each question has only one correct answer. Okay, choose the answer and write only the letter A to D next to the question numbers 1.1 to 1.10 in the answer book, and we are given a sample of how that goes. Okay, so let's go. 1.1 says, for which one of the following molecular formulae are chain isomers possible? Remember, the minimum is 4 carbon. You need a 4 carbon chain, okay, for you to be able to make chain isomers. Okay, so your carbon chain must be 4. Anything less cannot form chain isomers. All right, great stuff. So let's have a look at this one. This one is a C4, so that's methane. Okay, so most definitely that will do. All these numbers are lower than 4, so they definitely are not going to come into our rescue. So A becomes the answer. And then of course, if you want to visually picture it, so butane is something like this as a linear or straight chain, okay? But we can actually use a propane to form something similar, okay? So if you count the hydrogens in each one of these, it will be it will be H10, and then there's 4 carbons. So that's how you go about it. So a bit of basics are important. In fact, I didn't highlight our mental prep. Here is just logic, guys. Number 1, you need logic. 2, you just need all knowledge of chemistry. Okay, all of those things, they just come in here. So you need to be a bit logical and be in a position to apply or exercise all knowledge of chemistry. All right, next question. It says, which one of the following compounds has the lowest vapor pressure? Now we know that the lowest vapor pressure has the highest boiling point. Okay, and that has a strong bearing on the so-called intermolecular forces. So the type of the intermolecular forces involved is what determines these physical properties. Now let's look. A is a hydrocarbon, which is methane, which is essentially butane. So here we know we've got the London forces, right? Right. And then we come in here, we can see this is an aldehyde because the carbonyl group is at the end. So here we've got dipole forces, okay? Not a problem. in addition to London forces, of course. And then here we can see it's an alcohol, so it has hydrogen bonding in addition to London forces. Then here we've got a carboxylic acid with the COOH, and then of course we've got hydrogen bondings times 2 sites. Okay, so obviously the one with the highest boiling point is the one that will have, 2 sites for hydrogen bonding. So essentially it will have the lowest vapor pressure for the same conditions. So that's how you answer that question, nice and easy. 1.3, we're told here the type of organic compound formed when a haloalkane is heated in the presence of a concentrated strong base. We know here we're doing an elimination reaction, right? So if we're doing an elimination reaction, we form an alkene. Okay, so the answer is B. See, straightforward. And then we go on. Excess hydrochloric acid of concentration 0.1 mole per decimeter cubed reacts with 2 grams of magnesium under different conditions. Obviously, once you react an acid with a metal, usually we produce hydrogen gas plus some salt. So then it can serve as a reaction for which we can produce a desired salt. Now it says which one of the following combinations of conditions will produce the largest volume, so something got cut here, of hydrogen gas. So the largest volume in the first minute of the reaction. So this is a question on reaction rates. So obviously we're looking for a higher reaction rate. Okay, now the state of division, powder versus granules. We know powder will be superior to granules, right? Obviously we have eliminated 2 because they repeat, right? Right, so already we're dancing with A and C. Now a higher temperature is going to be favored over a lower temperature, so the answer here becomes C. We move on. The potential energy diagram for a chemical reaction is shown below. Obviously we can see that by the shape, this is an exothermic reaction where the energy of the products is it's lower than the energy of the reactants. Right. And then obviously what is the story then? That says which one of the following combinations is correct for the forward reaction. So we're looking at the forward reaction. We know that it is exothermic. Now delta H is always going to be X minus Y, the energy of the products minus the energy of the reactants. So X minus Y is correct. Anything otherwise already eliminates those possibilities. Activation energy, if we draw a line here, okay, so this is not a line that exists, but we want to use it. So we know that the activation energy is going to span only that portion. So essentially it's going to be Z minus X. Okay, so anything that says Z minus Y. Hey, so we've got Z and that one is already out. So obviously the potential energy of the activated complex is going to be Z. So C is therefore our answer. 1.6 says, consider the following reaction that reaches equilibrium in a beaker. So we've got this perchromate ion going to a dichromate ion. Then of course it's acidified and it forms water on the other end. So now I told you a few drops of concentrated sodium hydroxide, that is a strong base, okay, are now added to the beaker. So we know that a strong base dissociates completely to its ions, okay. So that is what is going to happen. Sorry, I'm making a mistake. There's no hydrogen, but there's going to be sodium plus ions. All right, so what's going to happen? Obviously, looking at the fact that sodium can be picked up by the dichromate ion and the perchromate ion. So essentially, they both can compete for the sodium, not a problem. But the OH will essentially react with our hydrogen. Okay? So that hydroxide ion will chelate our hydrogen ions there, all right? And that means the hydrogen ions are going to decrease. And if they decrease, Le Chatelier's principle says if we disturb this left-hand side, then the reaction that favors the reverse reaction will be favored. Now the question says, which one of the following combinations correctly identifies the disturbance on the system and the system's response? Obviously, we see that we will chelate our hydrogen ions, but this perchromate ion, not necessarily. That one does not necessarily really decrease because they each will share the sodium. So in a way, that will be balanced. Then which reaction are we going to favor is the reverse reaction, not the forward. Okay, so the answer is B. All right, not a problem. Now, according to Laurie-Bronsted theory, a conjugate base is formed when A or N, a proton is added to the acid. We really don't add a proton to the acid. An electron, we never speak of electrons, so that is out. A proton is removed from an acid. That is true. An electron is removed. Again, we never talk of electrons. So the answer there is easily C. Remember, we talk of protolysis, which is a transfer of protons, not electrons. Now consider the statement below regarding an alkaline substance. Okay, so an alkaline substance reacts with an acid to form a neutral solution. That's possible when a strong acid reacts with a strong base, or a weak acid reacts with a weak base. Okay, now turns red litmus blue, that is true. Forms a salt when it reacts with an acid, that is true. Now, which of the following statements above is always true? So now we want something that is always true. So what is always true is essentially this statement and that statement. This one is not always true because it depends on what type of an acid and what type of a base are reacting. Okay, so obviously our answer becomes D. Okay, great. So we move on. Consider the cell notation for a galvanic cell. Galvanic cell, we know that this notation, the left-hand side is always the anode, the right-hand side is always the cathode, okay? And then, of course, how do we know which side is which? It's the salt bridge. Okay, so we can see silver ions are being reduced, so reduction is taking place here. But here it's a bit of a mess, so we cannot be too sure what's going on. Okay, so it looks like we're taking hydrogen ions and these ones to form water, right? Because this is what is usually the case. And we know that this is essentially, is it oxidation? Yeah, this is oxidation. Let's just double check it, you know. Is it possible? I think so. I think so. But let's forget it for now. It's actually not correct what I'm doing. I wanted to do that. Okay, so I think that is oxidation because we do have water that oxidizes into hydrogen ions and these ions. Let's just double check. I don't think I remember this correctly. Unfortunately, these things will chow your time even though you're trying to keep it. Let's just have a look. Where is water? Where is this called waterpas? Where is the waterpas? Esan. It looks like it's a different story now, eh? Water, where are you? Okay. I don't seem to see the water. I don't seem to see it. There's lots of H2O's here, but these are not the ones. You see, there is water undergoing oxidation, but you see now there we've got OH minus. Yay when. Actually, what is going on is this one here. The way they wrote it. But in any case, we can see this is more of a stronger reducing agent than would be the silver there. So we always look. So how they write it, sometimes they write it to confuse us. So silver will essentially undergo reduction. This one will undergo oxidation because they told us it's a galvanic cell, so it should be a spontaneous reaction. Although they put it in a way that kind of causes a headache. But yeah, I can see their intention is just to confuse us rather than to relieve us. So usually we should be listing it from here. Yeah, whatever, man. Yeah, actually it is, you know, we're starting from this side to that side, so it's true. That is oxidation. Okay, now I told you which one of the following equations represents the half reaction taking place at the positive electrode. So we know that reduction is taking place. So that is obviously the silver picking up an electron. Again, a straightforward question there. So the last one, the concentrated solution of sodium chloride undergoes electrolysis. Okay, which one of the following combinations correctly shows the products formed at each electrode? Is it possible to form sodium at the cathode? True, because it becomes the negative terminal and sodium would be positive, so it's possible. And chlorine gas at the anode? Yes, it's possible because that becomes a positive electrode and it can attract the chloride ions, which are negatively charged. That can be oxidized to form chlorine gas. Can it be hydrogen gas at the cathode? It's true, because the H plus ions can be reduced to hydrogen gas there. What about OH? Is it possible for OH to form? Yeah, it's possible. So it's possible there. And in fact, this is possible when we actually oxidize water. Because water is a polar substance, right? It can pick up, is it 2 electrons, I think? It can form our hydrogen gas plus our OH minus. But of course, yeah, something like that, I believe. So, yeah, we will check. I think, if I remember correctly from what we just saw, that is possible. Okay, so now remember, this can form at the cathode only, but not at the anode. Okay, at the anode we would not form this guy. So as a result, this is not correct. Because it forms actually at the cathode, that OH minus. Can we form chlorine gas at the cathode? The answer is a definite no. So at the anode, we're not, because that can be reduced to these, not oxidized to these. Okay, so that is out. So at the cathode, yes, we can form these two guys. At the anode, we can form those two guys. Now we have a problem because we need to decide between A and D. Now we need to consult our electrode potentials and compare the chlorine and these other ones. So yeah, this one is taking their time. We did not want to lose. Now let's have a look. We said water, because this is a polar substance, because water is polar, it can be attracted to either terminal, be it the positive or the negative. But we're saying now at the cathode, water can be attracted and it can actually pick up 2 electrons and be reduced to OH minus ions. They forgot the negative there, and hydrogen gas. Okay, that is oxidized. This is oxidation. But now let's compare and contrast with the sodium. Where is sodium? Where is sodium? Sodium is over there. So if you're looking at sodium, sodium can pick up an electron to sodium, so that is also oxidation. But of the two, which one has a stronger oxidizing ability? It is water. So water will literally try to overtake the sodium. So we can see now that, well, the most likely scenario is that water will actually be the one oxidized than the sodium because of its higher oxidizing ability. And yet chlorine gas, the chloride ions, they forgot a negative there, so they will essentially be oxidized because that is sort of like reversed. So now we come back to say our answer here is essentially D because of the different strengths. So here, this is the answer. Okay, so we chose this one for our answer. So that is the story. So be careful. Questions like these, they always seek to destroy you. So you need to be careful on how you answer these questions. As much as sodium is possible, but the most likely is water being oxidized, being reduced to hydrogen gas and the OH minus, whereas this one gets oxidized to chlorine gas. So we are sorted, we are done. We get to question 2, which is now where action is. Okay, so as you can see here, you need to know a lot of chemistry for for section A. It's not section A, but question 1, okay? Now for question 2, you just need to know organic chemistry here. Organic chemistry, meaning know the IUPAC naming, right? Know the organic reactions, especially conditions. Okay, very important. And what else? I think this is essentially what is important. Perhaps we can say some simple calculations that can involve the empirical formulae, okay, and molecular formulae. So usually that's as far as this section would go. Okay, so let's go for it. We're told to study the table below and answer the questions that follow. Now we've seen here, this is a branched alkane, okay? So it's a hydrocarbon. Not a problem. This one, because of the OH minus and this being on the last carbon, so this is the primary alcohol. Okay, and then we look at this one. We have a molecular formula, but there's only one oxygen. So here we've got possibilities. This could be an aldehyde. Okay, it could be an alcohol. It could be a ketone. Okay, that is the possibilities. But if we look at the hydrophobic end of it, it says C4H8, which is CnH2n, and that eliminates the alcohol. So the alcohol falls off from the possibilities, and we're left with either an aldehyde or a ketone. This one, if we look at it, we will see that once we see a CH2, it is within the chain, it's not a branch. But of note is that here we are missing 2 hydrogens. We're missing one for the C and one for the last carbon. So that means there's a double bond somewhere between those 2 carbons. that makes it an alkene. Okay, this one is a hypothetical one, so it can be anything. It can be an alcohol, let's just say an aldehyde. It can be an alcohol, it can be a ketone, it can be an ester, it can be a carboxylic acid, etc. So this one has a lot of possibilities. It simply says, watch out, you might get caught pens down. Okay, so let's have a look. What is the story here? Define the term unsaturated hydrocarbon. So that is easy because this is stuff you guys already know very well. So we can say it's a hydrocarbon that contains a multiple bond within the carbon chain. Okay, it's a hydrocarbon that contains a multiple bond within its carbon chain. So a multiple bond can be a double bond, it can be a triple bond. So this is easy. Easy marks. So we've got 2.2. It says write down there. So here we're just writing down. So easy stuff here. So we've got 2.2.1. A letter that represents an unsaturated hydrocarbon. We saw that an alkene is letter D. So we've got D there. 2.2.2. The IUPAC name of compound A. Okay. Now compound A, we need to find the longest chain. So let's see, we've got 1, 2, 3, 4, 5, 6. If we go that way, 1, 2, 3, 4, 5, 6. If we go that way, straight 1, 2, 3, 4, 5. So the longest chain is 6 carbons. Let's just go that route. Now the question says, how do we name these ones? We always have to name the shortest distance. I mean, we have to number the carbons so that we get the shortest distance to the first branch. So if we come from this end, it's going to be 1, 2, 3. So this methyl group is on the third carbon, but if we come from this end, it's on the second. So this must be the first carbon, this must be the sixth carbon, so this is second, third, fourth, so that is the fourth carbon. Okay, so now to name our hydrocarbon, it's going to be 2, 4 dimethylhexane. Okay, so that's the name. I think we sorted it. So you're getting how many marks? 3. Wow. Maybe for these little things and then that word and that, but normally the substituents, they count for 1 mark together with their name and the parent name. So they decided to be a little bit generous. Okay, now the IUPAC name of the positional isomer of compound B. Of course, the carbon, this OH group can be here on the first carbon, it can be on the second carbon, but we cannot put it on this third carbon. That one is wrong because it's the same as the first carbon. So there's only one positional isomer there, which is going to be propane (2O). Okay, so it's either on the first carbon or on the second carbon. I can go, don't lay. What is that? All right, so that is the story there. So here 2 marks. So I guess we're getting a mark for the parent and the position of the OH group. Easy stuff. So 2.2.4 says the IUPAC name of compound D. Okay, so here we need to count the carbons. Of course, we've got a double bond between the first and the second carbon, so we count the lowest of the 2. So it's going to be 1 in, whatever it is. So how many carbons we've got here? 1 plus 4 carbons here, so that is 5, then 6, 7. So we've got a hept 2 in. I think there's no side branch here. It's a hept 2 in. Again, how many marks are we getting? The position of the double bond in the parent chain. So that is fine. So we've got 2.2.5. Says a balanced equation using molecular formulae for the complete combustion of compound A. Okay, now let's see how many carbons we've got there. 1, 2, 3, 4, 5, 6, 7, 8. Okay, we've got C8, 8. So obviously this is an alkane, so it's going to be 8 by 2 is 16 plus 2 is 18. Okay, but you can count here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Yeah. And then now once the word says complete combustion, it means we're going to add oxygen here. And then we are supposed to form carbon dioxide and water vapor. Okay. That is when we're doing a complete combustion. But an incomplete will be carbon monoxide and water. All right. So now we have to do some work. We've got how many? We've got how many carbons there? We've got 8 carbons. So we put them there. We're supposed to sort out these ones. So there should be 9 here. Now, we have a problem now because oxygen is going to be 8 by 2 is 16. 16 plus 9, that's 25, is it not? Yeah. So we've got 25. So we can put our 25 here. But we've got a problem because now the oxygens are 50 against 25. So what do we do there? We divide this by 2 to make it, balance. But now we don't have coefficients that are fractions. So we just simply multiply by 2 throughout. Then we're going to have here 2C8 H18 plus 25O2 going to 16 CO2 plus 18 H2O. Okay, so that's great because it sorts out our problems. But why do I feel like there's a crime now here? There is a situation that I don't like here. Yeah, man. Yeah. Let's see. We've got now 16 carbons. There's 16 carbons, okay? We've got 18 by 2. That is 36, eh? Yeah, there's 36 hydrogens. And then we've got 36 hydrogens. Then we've got 50 oxygens. Then we've got 16 by 2, that's 32, plus 18, that's 50. So everything is balanced. So this is your answer. Okay, so that is your answer. Of course, this one becomes your thought process. You do it in your rough work. Okay, you don't have to show it. You can just show the final product. But even if you show the steps, make sure you indicate that this is the answer. Okay, otherwise you're gonna run into some serious situations there. So there you're getting 3 marks. Okay, I'm not too sure where they are, but nonetheless we have 3 marks there. Now it says 2.3. Okay, what do they want? Now we're told the formula C4H8O represents 2 compounds that are functional isomers. Again, we can see here that we saw that obviously we're dealing with either an aldehyde or a ketone, which we know for sure they are functional isomers. And it says define the term functional isomer. Again, definitions, easy marks. These are compounds, organic compounds, that have the same molecular formula but bear different functional groups. Okay, so they have the same molecular formula but they actually bear different functional groups. Okay, so that is it, or you can say they belong to different homologous series. So easy 2 marks there. We move on. 2.3.2 says write down the structural formulae of each of these functional isomers. Okay, that's easy. So the first one is a ketone if we want. So we can say A, we can have 1, 2, 3, 4. And then we can make this one a ketone. Put our carbonyl group there. So these are hydrogens. Okay, so that's the first one. The second one is 1, 2, 3, 4. Our carbonyl group is at the end. Okay, so that's it. It is done. Okay, all right, okay. So that is it. So we're getting our 2 marks there. I guess the position of the functional group and the rest of the chain, again, same thing, and the rest of the chain is where we get our 4 marks. Okay, let's move. We don't have time. So we've got 2.4. 2.4 says a 2-gram sample of compound E, so that one is a big problem, right? Contains 1,09 grams of carbon. So obviously we're going to look for the molecular formula or empirical formula there. And 0,18 grams of hydrogen. And the molecular mass of 88 grams per mole. Okay, so what's missing here is oxygen. How many grams? Of course, we will follow the sample that they gave us, so that mass should help us to find that of the oxygen. Then it says determine the molecular formula. Okay, nope, determine the molecular formula of compound E by means of a calculation. So you can see here we are doing some work. Okay, let's start. So obviously we know that we want the number of moles. The first thing is that we want the number of moles of each, because these are molar ratios that give us a molecular formula. So the number of moles of the carbon, maybe let's write it here, of carbon is going to be the mass that we are given, which is 1,09, divided by the molar mass of carbon, which is 12 in the periodic table. How many moles is this? So 1,09 divided by 12 gives us a 0,091 to 3 decimal places moles. Okay, so you don't want to round off to 2 as yet. And then the next one, we want the number of moles of hydrogen. It's going to be the mass that we're given, which is 0,18 grams divided by 1, which is going to be 0,18 mole. Okay, not a problem. And then what do we want? We also want the number of moles of oxygen. Now the mass is going to be 2 minus the sum of these two, 1,09. I ran out of space, so I don't know why I was trying to force matters here. Okay, let's do it here. The number of moles of oxygen is going to be 2 grams minus the sum of these two. Okay, and then we divide by the molar mass of oxygen, which is 16. And then let's see how many moles that is. So we've got 2 minus 1,09 plus 0,18. Okay, be careful here. You can make a costly mistake, which is 0,046 moles. Okay, that's fine. Then now what do we know? We know that we need the molar ratio of these three. The molar ratio, we're always going to divide by the smallest, and the smallest is 0,46. So we're going to have basically okay, we're going to use carbon here, so it's going to be 0,091 divided by the smallest, which is 0,046. Okay, and then we're going to have here hydrogen is going to be 0,18 divided by 0,046, and then the oxygen one is going to be 0,046 divided by 0,046. Okay, great. So what is that? 0,091 divided by 0,046. So that is, now remember we round off to the nearest here. So this is 2. Okay, and then this one 0,18 divided by 0,046. This one is approximately 4. Okay, and then so we've got here yeah, that one should be 1. There's no question about it. Okay, so we can say there for the empirical formula is such that we've got C2H4O. Okay, so that's what we've got. Now, what do we know? We also know that now the ratio of molecular formula not molecular formula, but molecular mass over empirical mass is going to be, that is 88 over, this one is going to be 12 by 2 is 24 plus 4 plus 16. So let's see what we get. So 88 divided by 24 plus 4 plus 16, it gives us a 2. Okay, so we can say therefore the molecular formula is going to be 2 into C2H4O, which is going to be equal to C4H8O2. And if we have got 2 here, it can either be an ester or a carboxylic acid. Okay, so that is the story. So it's a bit of a long one. You know what? We did this calculation in our first year at university. I'm surprised you guys, even at grade 10 now, you are doing this. So you can see it's a bit of a walk to freedom, right? Right. So 6 marks. Of course, getting the number of moles of each one is a whole mark, okay? Not just one. Getting the ratio, their molar ratios, is another mark, okay? Finding the empirical formula is a mark. Getting the ratio of their molecular mass over empirical mass is important, and eventually doing those two. So this is 2, 4, 6. So that's it. Okay, easy stuff. So nothing really special there. So let's get on to the next question. Question 3 says, okay, learners investigate the boiling points of the 4 organic compounds given below. So we've got butanone, which is a ketone. Then we've got butane 1-ol, which is the primary alcohol. And we've got propanoic acid, it's a carboxylic acid. And then we've got 2-methyl propane 1-ol, so it's a branched primary alcohol. Okay, so what is the story here? For us to determine the physical property of boiling point, it already tells us that we need to consider the intermolecular forces, because those are the governors, right? Here we've got dipole-dipole forces. Here we've got hydrogen bondings. In addition, of course, to London forces. They all have London forces. And then here we've got hydrogen bondings times 2. Right here we've got hydrogen bondings here. But the only difference between this one and butane 1-ol is the fact that this one is globular, or it's branched, so it will have a lower boiling point than the butane 1-ol, even though they have similar intermolecular forces, but their strengths are differing, the London forces, of course. Okay, now it says define the term boiling point, 3 marks. So 3.1, we know that it is the temperature at which the vapor pressure of a substance is equal to the atmospheric pressure. Okay, great, easy, 2 marks again, nothing really special there. So definitions should be a way of scoring marks in each question, right? Because everything else can be a nightmare. Which compound, butane 1-ol or 2-methyl propane 1-ol, remember these are isomers of each other, and they are essentially chain isomers if you think about it, will have a higher boiling point? Fully explain the answer. Okay, so that is easy. So the one that will have a higher boiling point is butane 1-ol, so we go for it. Butane, oh, my butane 1-ol is wrong. Okay, butane 1-ol will have a higher boiling point. Now, how to explain that? We can say now, due to its straight chain, okay, maybe we can just say it has hydrogen bonding in addition to London forces. Okay, maybe let's just mention the strength. It's very important. So it has strong hydrogen bonding in addition to weak London forces, just like 2-methyl propane 1-ol. Okay. However, due to its straight chain, it has a larger surface area for the action of the weak London forces, making them stronger than for 2-methyl propane 1-O. Okay, the only difference is the London forces between the two, therefore more energy is required to separate the molecules. Hence, it's higher boiling point. Come on. It's higher boiling point than 2-methyl propane 1-O. Okay, the comparison is very important because you don't want to miss out on those things. Okay, okay, so I like to write a proper comparison so that I don't have to write too many things. Okay, so you could see here you're getting 4 marks. So we're getting a mark for choosing that guy. And then, of course, talking about the differences in the strengths of the forces. Sorry, mentioning the need for that energy. And essentially the correlation. Of course, this last mark you can give it for the first statement because this is already something we know is the case. We're just correlating. So this is how you score those marks, and we keep it going. So we're told here the curves P, Q, R, and S below are obtained from results of the investigation. Okay, so what do we see here? Remember from grade 10, in the heating curve, when the curve goes flat, this is when there's a phase change. Okay, remember that. There's a phase change when the heating curve goes flat, and that almost always coincides with the boiling point, you know, all those things. So here we're talking about boiling points most likely. Okay, great. So when the heating curve plateaus, we know we are at a phase change of some kind. And since we're investigating boiling points, so these are essentially the boiling points. Now it says, which physical property is represented by temperature X? That should be the boiling point of compound P because it's plateauing as well. So we're doing 3.3 actually. So we can say it's the boiling point of compound P. It's a specific one, so you have to mention that. It's not just for any other. Okay, 3.4. Okay, let's rush through this one. Now it says, which curve P, Q, or R? Okay, perhaps we don't really care. Property X is just the boiling point. Okay, we don't really need to specify because curve P is not necessarily a compound P. Okay, it's just a boiling point, no problem. And we've got here 3.4.1 for butanone. Now remember, butanone, if we list them according to their boiling points, first of all, we know here that butanone has dipole-dipole forces, so it's going to be this one. Okay, and then here, the next one is going to be the branched 2-methyl propane 1-O. Okay, And then here it's going to be the straight chain butanol or butane 1-ol. And then that would be the propanoic acid. Okay, so easy. So we saw butanol is going to be curve S. So that is S 3.4.2. For propanoic acid, it's going to be P. So 3.4.3 is this one. It's curve R. Okay, we can see that. And then now 3.5 says give a reason for the answer in question 3.4.2. What would be the reason there? Well, why does it have a higher boiling point? Essentially, we can say propanoic acid has 2 more sites for the action of strong hydrogen bondings in addition to weak London forces. That's it, because that's the only reason it has those things. It's just the type of the intermolecular forces it has. So you score your 1 mark. And that's how we squash that question. So let's quickly try and get through question 4. So here we need to be smart about reaction conditions, but let's explore. Now, the flow diagram below shows different organic reactions. P, Q, and R are organic compounds, okay? So we can see here that we've got compound P here. And then we've got compound Q here, which seems to be the center of all problems. And then we've got this lovely one here, which gives us an identity of all, because it is the clue to most of the things that we want. And then we've got this one, which is a major product, which already tells us we're going to apply some rule to know what that is. Okay, let's work it out quickly. If we see reaction 1, we are adding bromine to it, and then it gives us a 1,2 dibromo 2-methyl propane. So it gives us a haloalkane. So this one already says this is an addition reaction. Okay, and essentially it's a halogenation. Or you can say bromination to be specific, okay? Then this means this one is an alkene, okay? Because if we can add and both the bromide atoms are taken up, then it means that's an alkene. There's a double bond somewhere, okay? Then again, with the alkene, we are doing HCl. So this is hydrohalogenation, which is also an addition reaction. Okay, and then we are going to form a haloalkane. So this is also a haloalkane. Okay, now if we're taking a haloalkane to an alcohol, we are doing hydrolysis. Okay, which is a substitution reaction. All right, and we're doing here using a dilute base, dilute strong base. Okay, and then reaction 4, we are taking an alcohol to an alkene. That's dehydration reaction, which is essentially an elimination reaction. Okay, great stuff. So if you quickly look at those things, you are able to focus. Now this is 1,2 dibromo 2-methyl propane. So essentially the parent chain here is propane. So if we look at this one, it's going to be 1, 2, 3. But then on the second carbon, there's a methyl group. Okay? And now we know that if we add it, then there must be a double bond between these two. Okay, so we only have 2 hydrogens there, and we've got 3 hydrogens there. So that is the structure of that compound. And then if we look at this one, the major product, when we add HCl, we use Markovnikov's rule, MR. Okay, so Markovnikov's rule will tell us that we'll add the hydrogen to the carbon. If we're looking at the carbons that participate in that double bond, so essentially the carbon that bears the most of the hydrogens will have the hydrogen added to it, and then the one that has less will add the halide. So essentially it gives something like this. So here we're going to get the chlorine here, and then here the hydrogens. Okay, that is the stuff that we know is going to happen there. All right, let's quickly try and get through this one as fast as possible. Now reaction 1 is an addition reaction, most definitely. Write down the type, not necessarily. I don't like this kind of questioning, but I would prefer the name because the type is already addition, is it not? So we've got 4.1, so 4.1.1. This is now a halogenation. Or you can even write the specific name, bromination. Okay, easy one, Mark. You move on. 4.1.2, it says one observable change that occurs in the container during the reaction. You can just say the bromine water decolorizes. Okay, or it loses its color, because we know a haloalkane is colorless. So all of that brown color will disappear and it becomes colorless. Okay, now it says the structural formula of compound Q. We've already figured it out. So we've got 4.1.3. So it's 1, 2, 3. Okay, there's a double bond there we could see. Let's just put it under to avoid problems. So we've got that structure there, which is 2-methyl prop 1-in. That is the IUPAC name if you were to be asked. So here you're getting 2 marks. So the position of that and essentially the position of the side branch, I think so. This was worth 3 marks because the parent chain should also be marked, but anyway, they decided not to. Okay, now we're told here, consider reaction 2. Write down the IUPAC name of compound R. Okay, well, the IUPAC name of compound R is something like this. So this is going to be 2-chloro 2-methyl propane. Okay, that is the name. That is the name. Okay, so how many marks are we scoring there? Just 2 marks. Wow. Okay, that's fine. They don't care about the propane part. It's fine. We will leave them to that. So 4.1.5. Basically it says for reaction 3, write down a balanced equation using structural formulae for the organic compounds. Always remember that when they say use structural formulae, you only talk of structural formulae in this section for organic compounds. Forget about the inorganic compounds. As much as you know their geometric shapes, don't bother. It's not necessary. Only the organic compounds, you must use a structural formula. Okay, for the organic compounds, That is reaction 3. So we want to form that alcohol. Okay, so we've got 1, 2, 3. So we're just going to put our chlorine there, our methyl there. So indirectly they just want that structure, eh? These guys are sealing, eh? Plus, what do we add to that? Remember, we're going to treat it with a strong base, sodium hydroxide, but this one must be concentrated, so it has to be lying. It has to be dilute, okay, in alcohol. Usually we use ethanol. Okay, we treat ethanol with this thing, and then we put in our haloalkane. And then we're going to end up with our alcohol. Remember now, when we're doing a substitution reaction here, what we're going to substitute is the halide. Okay, so this is going to form us a tertiary alcohol. So it's going to be 1, 2, 3. So the OH will attach there. Still have our methyl group. Okay, and then of course here, please show that you are heating this thing as well. So plus, so what happens now when we lose our chlorine, it will pick up the sodium, so we're going to form NaCl. All right, great stuff. So that is how we sort this one out. So 6 marks, they're really silly, eh? But I guess here the position of our chloride ion and the rest of the molecule is important, and the state of our strong base, that it has to be dilute and it has to be in alcohol, and then the fact that we are heating the stuff, and then of course the position of our OH is important, and essentially the last one, because the rest of that molecule is a repeat. So 2, 4, 6. So it looks like we are sorted there. And then we've got 4.1.6. It says the IUPAC name of alcohol P. Okay, so this one is essentially 2-methyl propane 2-ol. All right, so this is 2-methyl propane 2-ol, almost like that previous one, which was 2-methyl propane 1-ol. So we're doing an isomer of that. Okay, all right, okay, that's fine. So it's a tertiary alcohol, essentially, this one. Great. 4.1.7 says, write down the type of elimination. Already this is the type, so probably they want the name of the elimination reaction, which is now reaction 4. Okay, so here we've got our position of the OH and the side branch, I guess. So reaction 4, it's a dehydration reaction, essentially. Okay, it's a dehydration reaction, which is straightforward. So 1 mark, yes. And then now we've got here 4.2. This question's got longer than I expected. Okay, butane 1-ol reacts with propanoic acid. So this is a primary alcohol reacting with a carboxylic acid. You know that we're doing esterification there in the presence of a catalyst, which is H2SO4, right? Yes, and then write down the type of reaction that takes place. So 4.2.1, we know that it is a condensation reaction. Of course, they allow you to faff around and say esterification. Esterification. I'm calling this one faffing around because they didn't ask you the name of the reaction. They asked you the type of a reaction. So always answer what is asked. Don't give us what we did not require. Unless you don't know what you're doing, and we will tell by just you doing stuff that... For me, I would penalize someone who says esterification because the question said type. But that is the name of the reaction, okay? Anyway, forget the nonsense. 4.2.2, it says now the IUPAC name of the organic product formed. Of course, from the alcohol, we'll take the alkyl group, which is butyl. And then from the propanoic acid, we'll take the propanoate ion. So it's going to be propanoate. It's an ester, okay? So you're getting 2 marks for each one. All right, so that's it. You're getting your 18 marks, a very long 18 marks. All right, guys, so that is cool. Let me just drink some. Okay, guys, so let's carry on. So you can see here, if you can, in the first hour, to have answered all these first 4 questions, probably you would have done very well indeed. But yeah, sometimes it's not that easy, eh? It's not that easy. So let's look at question 5. Okay. So question 5 is now what you call reaction rates. So here, just know the factors that affect the reaction rate. Okay, that is very important. And then, of course, know some stoichiometric calculations. Okay, know all of those things. They're very important. And then, of course, just general chemistry. You may need a bit of logic, because maths is applied in here, so it's a logical question as well. So this is some of the things you might want to think about when you're dealing with this one. Let's continue. It says consider the following decomposition. Okay. Reaction that takes place in a sealed 2 decimeter cubed container. So when you're given the volume, you're most probably going to need to use it. Now we're given here 2 molecules of dinitrogen pentoxide, which decomposes into 4 molecules of nitrogen dioxide gas, which is brown, and oxygen, which is colorless. I believe that one is colorless as well because of too much oxygen in there. Anyway, I don't know. Whatever. The graph below shows how the concentrations of dinitrogen pentoxide gas and nitrogen dioxide gas change with time. Now, of these graphs, which one belongs to which? Obviously, this one should belong to the dinitrogen pentoxide because we started somewhere. Okay, we started somewhere, but for the product, which is nitrogen dioxide gas, it definitely will start from 0 because at the beginning there's nothing, but at the end there is definitely something. Okay, so we know that this one should represent our nitrogen dioxide. Oh, you can't see, ne? Maybe let's make it black. So that would be nitrogen dioxide, and that would be dinitrogen pentoxide. Okay, not a problem. So what is the story? Of course, we're using concentration. Again, look at the unit of measurement that we're dealing with, because it hurts if you don't pay attention to that. And then time is in seconds. Again, pay attention to the unit of time used so that you don't run into a few issues. Now, what do we see here? We can see that, well, as this one decreases, the other one increases. Not a big deal. But what is the significance of these things? Why are they plotting these points? Well, maybe for comparison purposes. We will see. It says refer to the graph above and give a reason why curve A represents the change in the concentration of nitrogen dioxide gas. I mean, it's the product. Initially there was nothing, but as this one decomposes, it will form a product. Okay, so the answer is we know that I don't know how to answer this question. Why? It's because the graph, okay, we can just say the curve starts from 0 to a particular concentration, right? Meaning it's the product of the decomposition of N2O5. So you can just try here to make sure you don't lose that one mark by making sure you're forcing the one who's marking to listen, even if they are trying not to listen, because some questions are pretty vague. So when the question is vague, you just put as much effort into answering it in the best way possible. Otherwise, yeah, that's the story. Because if it doesn't start from 0, then it's not a product, is it not? Because initially there's no product, there's just a reactant. Eventually there will be a product and maybe less of a reactant or even no reactant anymore. Okay, consider the statement below. The rate of decomposition of N2O5 is half the rate of the formation of nitrogen dioxide gas. Okay, is this statement true or false? Give a reason for your answer. That is strange. Perhaps this is where these plots come in. And then again, if we try to approximate that plot, okay, these plots are a bit crazy. So here it's a bit of an approximation. I don't know. But what I would choose is this one right here. You can say that plot looks like it's coming through there. So, I mean, guys, it's ridiculous, is it not? Perhaps this one, because the plot has to intersect the graph, maybe there. And then when we look at this plot, it intersects the graph where? Yeah, maybe there. So you see when these plots are not so nice and accurate, but I think I messed them up as well, so it's fine. We just look at the first, say 100 minutes, because that would be 100. It doesn't matter, you can look through the entire thing or you don't, it's up to you, honestly. So I don't know, guys, but maybe let's just look at the entire thing because we just want the average rate. Maybe it's safer to do that. And then if you're looking at this plot, it's going on this line. It's exactly that same line that we're dealing with. So that line there, it's 50. So 50, how many small blocks? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 50 divided by 10 is 5. So this is going in 5s. So this is 55 and 60 there. So that is 60. And then if we're looking at that last plot there, it's following this line. So these things can be a bit tedious. So this is 255, 60, 65, 70, 75, 80. So that is 280. So now we need to compare these rates because we're looking at the graph, right? The rate for the NO2, remember, it's going to be the change in concentration, which obviously came from 0 to 280. So we're going to have 280 times 10 to the minus 4 because there is that little multiple there, all over the time that it took for that reaction to get to that last plot. So this is 700 over 700. So let's see. Unfortunately, these kinds of questions, there's no beating around the bush here. You just have to do what you have to do, and you just live your life as best as possible. So here I'm getting a 4,5 times 10 to the minus 5 mole per decimeter cubed per second. Okay, so that's what we are getting there. And then let's look at the rate of the dinitrogen pentoxide decomposition. This one you already multiply with the negative because there's going to be a few issues there. So that is 60 times 10 to the minus 4 minus 200 times 10 to the minus 4 all over, say that time is 700 as well. So let's see, minus into 60 times 10 to the minus 4 minus 200 times 10 to the minus 4 divide by 700. This one gives us a 2, 0 times 10 to the minus 5 mole per decimeter cubed per second. Okay, so if you look at these two, you can already tell that one is higher than this, because I mean 4,5 divided by 2. Okay, let's just do it. 4,5 to the minus 5 divided by 2 times 10 to the minus 5 as well is basically 2,25. So it's essentially rounded off to the nearest is 2. So definitely it is true. Okay, so what we can do here, we can then say, okay, we can say the answer here is that is true. Okay, it is true. But then what is the reason? Angazi ke manje ukuthi reason yethu sothi kwenze njani. I don't know, guys. Well, we can say since you can say, Yabafet, how do you answer this question? It's difficult, is it not? It's truly difficult. Yeah. It's a little bit silly. And I don't know what I'm gonna say, guys, because the reason can be anything, is it not? We can use a calculation because it said etc. this thing. So yeah, some questions are crazy, man. I would love to know what is their reason. They can say the reason is that the rate of nitrogen dioxide is, which is there for 2 times. So we can say therefore the rate of nitrogen dioxide gas production is double, just over double the rate of dinitrogen pentoxide decomposition. Of course, guys, I don't know what is the best way here. Perhaps we can look at the mass or the concentration arrived at in some moment. You can either look at the entire concentration from the beginning to the end and the entire concentration of that one as it decreases and see how much this one dropped over the other one. But I think without a calculation you wouldn't know. Okay, so I don't know, or maybe you can just pick a point. For example, this one here at 100 degrees, we see there that the concentration of our dinitrogen pentoxide dropped by how much? So this is 55, 60, 65, 70. So by the way, this is going to be now 170. So let's say 200 minus 170 is 30, right? Right. So it dropped by 30, but now this one has moved up by 60, you see? So 30 divided by 60 is essentially a double. So you can say here, since the concentration in the first 100 minutes of dinitrogen pentoxide dropped by 30 times 10 to the exponent 4 mole per decimeter cubed, whereas that one climbed by 60 times 10, which is of course a double, you know. There's plenty of ways we can look at it. You can either do this calculation. I mean, it looks hectic, but at the end of the day, we essentially have something. So maybe to avoid this long little thing here, let's just be smart about it and just use the graph to our advantage to not run into problems. Okay? We can say it's true. Why? Because the concentration of dinitrogen pentoxide dropped by 30 times 10 to the minus 4 mole per decimeter cubed, whereas their concentration of nitrogen dioxide gas increased by 60 times 10 to the minus 4 mole per decimeter cubed in the first 100 seconds. Okay, I mean, that you can tell that obviously 60 versus 30, that is double. Okay, so that is true. So maybe that one is the best reason to put forward than this long lengthy calculation. Perhaps those little marks, they were there to give us an idea of what is going on. So the change in concentration is the rate essentially. So let's just say that. So we're going to get our mark and then that mark. Great. Okay, we refined it. Yeah, but it's one of those nasty questions here because they can really throw you off if you're not careful. Now 5. This is 5.2. So now we've got 5.3. Okay, let's move, guys. I think we're wasting time. Calculate. Okay, so you see there will always be some small onion calculations. The mass of nitrogen dioxide gas present at the container at 400 seconds. So there is 400 seconds and that is the mass. The mass is exactly 200. Sorry, the concentration is 200 times 10 to the minus 4. So we know that if we want the mass, we know that concentration is equal to mass over molar mass multiplied by volume. Now the concentration there is 200 times 10 to the minus 4 equals what we're looking for. The molar mass of nitrogen dioxide is basically 14 plus 32, and then we're multiplying that by 2 because the volume was given as 2 decimeter cubed. So we can say here, doing our gymnastics of our famous cross multiplication, we can make a conclusion that the mass is going to be 200 times 10 to the minus 4 into 14 plus 32 times 2, which will give us what we want. So 200 times 10 to the exponent minus 4 into 2 into 14 plus 32. So you see your calculators are wonderful. So we're getting 1,84 grams. That's it. Simple stuff, simple stuff. So formula in physics, you get a mark. correct substitution, you get a mark. But let's just see, is it really the substitution? Perhaps not, because I think this calculation is a mark on its own, and spotting that is a mark on its own in the final answer, because the 2 decimeter cubed was given. All right, great. So we move on. Now that little crime happened again. So we've got here 5.3.1. So let's say 5.3.2. Says now the average production of oxygen in mole per decimeter cubed per second. Okay, in the 700 seconds stuff. Okay, so basically here we can use the friend to compare the two, because this can only happen in principle or theoretically, because we don't have any other tool that we can use. So 700 seconds, we're looking at 280. Okay, so that's fine. What we can say here, we will say this. We want the concentration of the oxygen is going to be equal to, now the stoichiometric relationship is going to be a quarter of the concentration of nitrogen dioxide gas. So that is what we need. Of course, these are molar concentrations, so you can safely do this. But if you wanted, you could go around the long route, do number of moles. It's not a big deal. So this is a quarter of, now this is 280 times 10 to the minus 4. So let's see. Now I've got a quarter of 280 times 10 to the minus 4. Okay, so this is now 7 times 10 to the minus 3 mole per decimeter cubed. Okay, that's fine. So now what did we want? We're looking for the average rate of production. So essentially we can say this implies that now the rate of O2 production is going to be equal to the change in concentration, which is now 7 times 10 to the minus 3 divided by the time, which is going to be 700 seconds. Okay, so sometimes, yeah, do you really want to write a formula? Yeah, perhaps. Yes. I hate this though. Change in concentration over change in time. So this is 7 times 10 to the minus 3 over 700. Okay, let's just put down the answer there to save our space. So this is 7 times 10 to the minus 3 divided by 700. So this one is 1 times 10 to the minus 5 mole per decimeter cubed per second. So that is the story of where to. So you can see here that our mental preparation is really doing the things, you know, the things that can be done when it matters the most. If you don't take this into cognizance, you're going to die. So usually a 4-mark question is either a very complex equation that you can use with many things inside it, or it's 2 steps. And as you can see here, we needed 2 steps. So first of all, this situation is important, and that is important, okay? And then essentially what now also matters is the story here, the answer. I am not too sure, but they can gift you the formula to make up for the 4 marks, because that substitution is already too obvious, is it not? I believe so. But anyway, the marks can be anywhere. Okay, let's end this pain quickly. 5.4 says the Maxwell-Boltzmann distribution curve for the dinitrogen pentoxide gas initially present in the container is shown below. All right, that was the initial stuff. Okay, now it says the initial concentration of the dinitrogen pentoxide. Sometimes we call this one a nitrogen anhydride. All right, or just simply nitrogen pentoxide is now increased. Okay, once we increased the concentration, what happens to the molecules? They increase. Okay, so it says now redraw the distribution curve above in the answer book and label this as P. On the same set of axes, sketch the curve that will be obtained for the higher concentration of dinitrogen pentoxide. Label this Q. Obviously, we're going to start from here. We go to a higher peak, and then that is the story that we're going to get. What is important here is to notice that the peaks, there's a higher peak because of a higher number of particles. Of course, this is not a line that exists. I'm just using it to teach you a thing or two. So the peak is much higher. Again, in fact, for every little thing except 0, for every little thing after that, we know that there's going to be more particles with that same energy in the next scenario than the previous. So that would be our curve Q. So here we can say 5.4.1. We can just say C graph. Okay. Now we've drawn it, so we're getting our marks there, 2 marks. I guess the shape and the peak, whatever, doesn't matter. Now it says, will the rate of decomposition of dinitrogen pentoxide at the higher concentration be higher than, lower than, or equal to the original rate of decomposition? Explain the answer. Obviously, it has to be higher than, right? Yes, it has to be higher than. So, 5.4.2, it has to be higher than, right? Because there's more molecules, then there's going to be more regular. You can just say more molecules in the container yields more regular effective collisions between the particles. Okay, and therefore a higher rate of the reaction. Okay, that's it. I mean, they didn't want too much, so that is the story. There will be more molecules. Of course, here you're getting a mark for choosing a higher than, and then we're going to get a mark for more effective collisions and that correlation to a higher reaction rate. So easy stuff. And then let's move on to question 6. So you're always told to start on a new page. So let's do it. Let's follow the instructions. Let's try and swallow this one up as quickly as possible. So we've got 1 mole of pure hydrogen iodide gas. Okay. And then now it's sealed in a 1 decimeter cubed container at 721 Kelvin. So that's a temperature. Now the equilibrium is reached according to the following balanced equation. And then of course here, the tools that you need is to know this guy. Le Chatelier's principle. Please sing it like a recitation back in preschool, okay? Second thing that you need here is to understand the calculation of the Kc. Of course, it uses basic stoichiometry. But the questions can be a silly mess, okay? And then, of course, understand the so-called dynamic or factors that affect equilibrium. Okay, so please know these things. Of course, general chemistry is very important, issues of common ion effect and stuff, but this is all going to fall under the factors that affect equilibrium. So perhaps you can add here the graphs. The graphs can be a mess if you don't understand them. So these are some of the things when you study for this section, you want to make sure you've tied the knots on those parts. The rest becomes easy. Okay, let's go on. So we're told it is found that 0.11 moles of iodine gas or iodide gas are present at equilibrium. Now state Le Chatelier's principle. Easy marks. Again, we can say when a disturbance, disturbance 1, when a disturbance is introduced to a chemical system in equilibrium, the system will shift so as to cancel. How do you write cancel, by the way? To cancel the effect of that disturbance. To establish a new equilibrium state. Of course, you can sing here and indulge as much as you can and show us that you know the English is problematic sometimes when you don't capture the words that are important, okay? But either way, here it's trying to say if there is a problem, you try to reverse it, right? Think of yourself when someone bends your tip of your finger. What do? You retract because you're trying to cancel the effect of that thing. So it's more or less something like that. Okay, so you just think of such situations and then you formulate the words, or you cram these things, but I do not support any form of cramming. It is dangerous because when you cram, you already don't understand. But when you understand, you don't even need to cram because those things are just going to come back to you. You have a lot of analogies to use to bring back all the information. Okay, let's keep moving. The story says now, determine, of course, a determination you know already from paper 1 maths, can be by calculation, by inspection, whatsoever. So let's see, determine the number of moles of each of the following at equilibrium. Okay, now the hydrogen gas, all right? Okay, all right. Hydrogen gas is one of the products. So if it is the product, obviously, we know that this is a 1-to-1 ratio, so the number of moles should be the same, right? Right, so 6.2.1. So we will know that the number of moles of hydrogen gas is going to be the same as the number of moles of the iodide gas, which is going to be 0.11 moles. Great, so that we're just using our molar ratios, so that is easy. Of course, you get your mark. So 6.2.2. We want the number of moles of hydrogen iodide gas. Okay. Now that one is a bit of a tricky one because look, if we formed this much of the products, the ratio is 1:2. So obviously, this means for us to go back, we're going to use the change. So this is going to be 2 times the number of moles. No, wait. We started with 1, so it's going to be 1 minus 2 times the number of moles of the iodide gas. I mean, we use what we were given. So this is going to be 1 minus 2 into 0.11. So let's sort this one out. So this is going to be 1 minus 2 into 0.11. So we're getting a 0.78 moles. All right. Great stuff. So we sorted over there. So let's try, guys. I need to take this one down quickly. It will take our time if we do not. So again, just 1 mark. Wow, that is ridiculous. Anyway, so let's move on. 6.3. 6.3 says the equilibrium constant at 721 is 0.2. Okay, so 0.02. Now the temperature of the container is now increased to 850 kelvins. And what happens? Our Kc value increases to 0.09. So if Kc increases, knowing that Kc is the concentrations of the products over concentrations of reactants. So if Kc increases, it means these ones increase when we increase the temperature. So essentially saying we are favoring the forward reaction. Okay, great, meaning the forward reaction is endothermic. Now, is the forward reaction exo or endo? The answer has already been established. So 6.3.1, it must be endothermic. It is endothermic, okay? Easy mark. 6.3.1 says, fully explain the answer to that question right there, okay? Well, first of all, it says the story. It says, now we can see that since Kc value increased with an increase in temperature, implies that the concentrations of products increased since Kc is equal to the concentration of products over concentration of reactants. Okay, so you throw in everything, so it implies that the concentration of products increased since, okay, Kc, I don't know why Berlin doesn't appear the line, since Kc is given by that expression, and we know that the forward reaction, okay, we just say, then we know that increase in temperature favors the endothermic reaction. Okay, obviously, that is the story. That is the story. So we can stop there. I mean, there's just 3 marks there. But all we needed to do was to first establish the part that says, well, the concentrations of the products increased. And what explains that is that. So if we increase the numerator, that ratio increases. Okay? So you can even put an arrow there to show that this is what happened. You're throwing everything. And this one is obviously the case. An increase in temperature always favors the endothermic reaction. Okay, so we can say therefore the forward reaction is endothermic. Okay, so you're going to state all those things, but you already have your 3 marks. But you always must make it a must that you have a conclusion. A conclusion that correlates with the statements above, okay? Even though you may not get a mark for it. Okay, now this big one, this one. Calculate the mass of hydrogen iodide present at the new equilibrium at 850. Okay, so this one is the big one. So this is the one that you guys need to practice as many of the questions around it as possible, because it carries a lot of marks and there's no reason for you guys to get it wrong, because it's always there. It's always there. So there's a lot of videos I have made on this section. You should go to them and learn as much as possible, and there's plenty of people showing how to work out those problems. So there's no need for any student to miss out on these ones. For me, this is a guarantee of big marks. Yes, it's going to challenge you, but at the same time, a chemistry student should not suffer here. It can only take a mistake or a slight misunderstanding of some issues that are provided, but you should not walk away with less than 50% of this question. Please make it a point that even if you don't get full marks, but 50% is stuff you score. Okay, my battery is trying to escape me, so I'm going to try to connect my thingies to the thingies. But let's end this question before we lose too much time. Okay, let's do it. Let's do it. Now we have to work a bit. Now the issue is we take our equation. So we've got our 2HI, all right, so these are all gases. Very important. So we know that initially the number of moles was what? Is what we have from the previous equilibrium. So 0.78, right? And then for these ones, we've got 0.11. Is it not? The change of the number of moles there, we can say it's x, so that is going to be a half of x. So please, molar ratios must be already second nature for you guys. So now we know that at equilibrium, what is the story there? This is going to be 0.78 minus x. Here we're going to have 0.11 plus 0.5 x. So we've got 0.11 plus 0.5 x. And then of course the concentration at equilibrium, the molar concentration, because this is 1 decimeter cubed, is just going to be the same thing. Okay, so that is easy. So we've sorted that one out. So we will do this stuff right here. We want to work out, this is the guy of interest, because if we know what that value is, it will help us to find the mass. So we start. Kc is given by the concentration of hydrogen gas multiplied by the concentration of the iodide gas divided by the concentration of the hydrogen iodide gas, but that one is squared. Okay, this implies what is the value that they're giving us? 0.09 equals, this one is 0.11 plus 0.5x into 0.11 plus 0.5x over This one is 0.78 minus x, but then that is squared. And then we can simplify this a bit. This is the same as 0.11 plus 0.5x all squared, all divided by 0.78 minus x squared. Now here, it's much easier to just take a shortcut of just taking a square root here. Because if you just take the square root here, the only reason though it's possible is because we've got squares in the numerator and denominator on the right hand side. We're just trying to avoid running through quadratics. So I don't know. What is this thing doing now? Hey, anyway, so we're just trying to avoid a quadratic because it's going to be a long, but don't get comfortable with shortcuts. Sometimes you have to go the long route. So be comfortable going either way. So when you practice, do both methods. Don't be happy you just got a shortcut. So now the square root of 0.09 is 0.3 equals, this is going to be 0.11 plus 0.5x over 0.78 minus x. Okay, not a problem. So we do our famous gymnastic here of cross multiplication. So basically 0.3 times 0.78 gives us a 0.234 minus 0.3x is equal to 0.11 plus 0.5x. Okay, and then we sort it out. We know that we're going to have to transpose this to that side, so it's going to be 0.5 plus 0.3, which is going to be 0.8. So this is 0.8x equals, we're taking that to that side, so it's going to be 0.234 minus 0.11. So this gives us a 0.124. Therefore, we divide by 0.8 on both sides. It means our x is going to be, this is 0.155 moles. Okay, because that was the change. All right, okay, all right. Now that we have the value of x, it means this implies that the concentration, what do we want? We want the mass. This implies that the concentration, do we really want the concentration? We want the number of moles, man. This implies that the number of moles of hydrogen iodide at equilibrium is going to be 0.78 minus 0.155. Okay, so 0.78 minus 0.155. This gives us a 0.625 moles. We can say, therefore, the mass, okay, maybe let's write a formula. So we know that this implies that the the number of moles of hydrogen iodide is going to be equal to the mass over molar mass. Therefore, the mass is going to be number of moles multiplied by molar mass, which is 0.625 into, this is 1 plus, this is 127, right? Right, you've worked with iodine so much that you need to know it by heart, okay? If you don't, uzovhinga tuyabizwa ke mntakwethu. In fact, that is just 128. So this gives us 80 grams. Wow, that's a lot. That's quite a lot. Anyway, so this is one of those questions that honestly are approachable, but they can challenge you because there's a lot to consider. Now let's go for it and say where are the marks? Basically, by working our table, introducing the x there is important. In fact, you can just simply say this whole shenanigan there, the change, we're awarding you a mark for it. And then, of course, writing a formula in chemistry is always, the things that can be done, okay? Then perhaps we can say you already have a mark for calculating those concentrations. And then for substitution, you always get awarded. So 4 marks for nothing, honestly. And then doing the gymnastics, rounding up to the value of x, 5 marks. Working out the number of moles, 6 marks. And then getting this one, 1 mark. Calculating the molar mass, that's the 8th mark. Okay, so these marks can be anywhere, but this is the stuff you need to know. And I can tell you guys, if you pace yourself so well that at least by the time you finish your 2 hours, you have gotten into question 7, you probably are going to make it. But obviously, there will be questions that you will skip. Try to speed up just right so that you have around 30 minutes to spare so that you can actually, make sure you do check some of the questions that you think will be challenging, to try and make sure you're writing the proper things and you're submitting a good attempt. Okay, so let's do question 7. Okay, question 7 is acids and bases. So again, what would you need to do in general for this section? Already, just know acid-base reactions. For example, when you're taking a strong base plus a strong acid, that you're going to get a neutral salt plus water. Okay, just know acid-base reactions like that. That's just an example. What happens when you react a carbonate, for example, a metal carbonate and an acid? You will form a salt, water, and carbon dioxide. Just remember those things. And then 2, know the models. That is the Lorentz-Bronsted model and the Arrhenius model, okay? Make sure you know what those models are saying, okay? And then, of course, stoichiometry. We'll take you through the harder questions. It's very important. And then know information about indicators. These ones are easy to remember, so you may want to perhaps revise a few of these even shortly before you write an exam, because it's not harmful to do so, but it may be useful in case a question is popped on those things. Otherwise, guys, general chemistry is very important. Even KC, but we're talking about ionization constant, but it's the same thing as the KC calculation. But here we talk about a ionization constant, which is, we could talk of KW. But whatever, man, these are some of the things that you want to put in order as you approach these kinds of sections. And you study those to make sure you understand them very well. Okay, let's go. Question 7 says the conductivity, okay? Once we talk of conductivity, is the ability of these solutions to kind of, conduct electricity. Okay, the conductivity of 3 acids, A, B, and C, are shown below. As shown below, is investigated at the same temperature, okay? Fine, trying to suggest that, well, we're more or less suffering the same rates of reactions, but it's fine, it's not really true. Anyway, we can see here we've got 1 mole per decimeter cubed of sulfuric acid, okay, which is a diprotic acid. And then we've got 0.1 mole per decimeter cubed of nitric acid, which is a monoprotic acid. And then we've got the weak dude, ethanoic acid or acetic acid. It's a weak one. Okay, but same concentrations, same temperature. Now the brightness of the bulb in the apparatus shown below is used as a measure of conductivity. Okay, so the intensity of that brightness will tell us whether this one is highly conductive versus the others. All right, there we've got, so there's our light bulb right there, and then we've got our battery there, then we've got our solution, obviously. Okay, not a problem. Let's see. It says now the acid solutions are electrolytes. True. Now it says define the term electrolyte. Again, easy marks. So we've got 7.1. So we've got 7.1.1. So now an electrolyte basically is a solution of ions, or it's an ionic solution. Let's just say it's an ionic solution. It's an ionic solution of a substance that can conduct electricity. Okay, that's what an electrolyte is in simple terms. So you walk away with a free 2 marks there. Okay, so now it says the brightness of the bulb for each of the solution is compared. Now 7.1.2, we're told in which solutions A or B will the bulb be brighter. Well, if you're looking at this one, sulfuric acid is a strong acid that dissociates to 2 moles of hydrogen plus ions plus the sulfate ion. Okay, so in essence, we end up with 3 ions in the solution. Okay, what about this one? Nitric acid will only give us 1 mole of hydrogen plus ions plus the nitrate ion. So we only get 2 ions in essence. So the more the merrier, right? That is the story. 2 against 3. So the more the merrier. So obviously sulfuric acid should be the one. So we're going to say A. Why? We know that H2SO4 is a strong diprotic acid compared to HNO3, which is a strong monoprotic acid. Can say therefore H2SO4 yields more ions in the solution than HNO3. We can say hence a higher conductivity. Okay, so guys, here you just try your best and say as much as possible. Of course, we're just campaigning for 2 marks, but you say things that matter. Of course, choosing A is, the mark. And then, of course, they said we must give a reason by referring to the types of acids. Okay, so of course, we spoke about the strengths of the acids. So perhaps a half a mark for that. And then the number of ions, again, another half a mark, which makes up the 2 marks. Of course, this is just a conclusion. For it, you don't always get marks. But yeah, that is the story. So that is the reason there. So 7.1.3 says in which solution B or C will the bulb be brighter? Obviously B. Again, give a reason by answering, for the answer by referring to the types of acids. Again, we know that HNO3 is a strong acid that than CH3COOH, which is a weak acid. We can say now HNO3 ionizes completely to form more ions than CH3COOH, which partially ionizes to form less ions. Therefore, HNO3 will have a higher conductivity than CH3COOH. I think that is the best argument I can put forward here. Again, choosing B is important, and then of course half a mark mentioning their strengths and their ability to ionize is another half a mark. The final one is just a conclusion that you must always have, even though you may not necessarily get marks for it, but it has to be some sort of a logical, answer to the big situation. Okay, let's move. We've got now 7.2. Says now a hydrochloric acid solution is standardized by titrating it against a 25 centimeter cubed of a 0.04 mole per decimeter cubed of sodium bicarbonate solution, which is Na2CO3. Again, we essentially needed to know how to make up this. They would give you the name, you'd have to come up with the formula. But anyway, you guys are spoon-fed and spoiled. It's all right. At the end point, now once you talk of the end point, it is found that 19.5 centimeter cubed of HCl has reacted. Okay. Now it says the balanced equation is this one. Again, this was the stuff one had to know. That when you react an acid with a metal carbonate, you're forming a salt, carbon dioxide, and water. You had to also balance the equation by understanding the molar ratios with which these ones have to combine. Anyway, calculate the concentration of the HCl. Since we reached some end point, so this is a complete titration, so we can use our stuff there. That 7.2.1, we know that the concentration of an acid multiplied by the volume of an acid, concentration of a base multiplied by the volume of a base, is the number of moles of an acid over the number of moles of a base. So that formula, you only use it when these completely neutralize each other, or else you're going to be in trouble. So what is the concentration of the acid is what we want. The volume of the acid, they told us, is 19.5. Here you don't have to change it to decimeter cubed because this is a ratio, so they will cancel each other out nicely. So here we were told this is now 0.04 into 25, equals, now what is the molar ratio here? Is 2:1. Then we do our famous gymnastic cross multiplication. Therefore, we can make a conclusion that the concentration of the acid is going to be equal to 2 into 0.04 into 25 divided by 19.5. Therefore, the concentration of HCl is that one. So let's do it. 2 into 0.04 into 25 divided by 19.5. So this is 0, 1, 0 mole per decimeter cubed. Remember, we said here minimum 2 decimal places, so we can do round off because this is a question on its own. Okay, 3 marks. Okay, formula, substitution, answer, straightforward. Everything was given. You never needed to do some intermediate steps. Okay, 7.2.2 says, now suppose a few drops of water were present in the burette before it was filled with the hydrochloric acid solution. Okay, not a problem. Now, will the volume of the hydrochloric acid solution needed to reach the endpoint be affected? Sorry, how will the volume of the HCl solution needed to reach the endpoint be affected? Another vague question. Choose from greater than, smaller than, remains the same. Give a reason for your answer. Yeah. Okay. But actually what reacts here is not necessarily a volume. What matters is the number of moles. So in essence, if there was just a few drops of water, they would just decrease the concentration, but the number of moles will essentially be the same, you know. So for me, I don't know if I'm answering this correct. I'll just say remains the same. As the number of moles of acid needed will be constant. Okay, I don't know, guys. This one is one of those vague questions. You either get it right or not. So this is where you want to double check with your memorandum. This is a 2 marks that you can actually lose easily because it's a very vague question. I don't know if I'm getting it correctly or not, but for me, what matters is the number of moles than the actual volume. Because remember, this was in the burette. It does not affect the number of moles we extracted from the original container of the acid, which is essentially what we needed. That volume transmits a certain number of moles, but itself is not really an ideal necessity, so to speak. Anyway, let's move on. Sometimes some questions are just like that. So 7.2.3. Now we're given a situation that you already love and know. I told you a concentrated household product clean contains ammonia. So what do we know here in RSA is handy, Andy. That is the stuff, right? It's handy, Andy. And by the way, this is my second name, but I don't use it because I don't even know what it means. It's not even a shorthand for Andrew or something. It's crazy, is it not? Anyway, so as the main cleaning agent, fine, to determine the amount of ammonia present in a 1 decimeter cubed volume of clean, the following procedure was followed. 20 centimeter cubed of clean was added to 250 centimeter cubed flask. Okay, so we're actually diluting this thing. Okay, the flask is then filled with 250 centimeter cubed, sorry, to the 250 centimeter cubed mark with distilled water. So we're definitely decreasing the concentration. We're diluting it. Okay, there it is. So we kind of put our clean, and then the clean is that little portion there. That is the 20 centimeter cubed. Then when we pour water, so we actually diluted the thing into that volume. Okay, not a problem. And then now I told you the diluted solution is titrated against HCl solution of the concentration calculated in 7.2.1. So that is 0.10 mole per decimeter cubed. Okay. Now during the titration, 22 centimeter cubed. Hey, I said needs nalento. 22 centimeter cubed of the diluted chem clean is neutralized by 18.7 centimeter cubed of the HCl solution. Okay, so we know more about the acid than the chem clean. So all we want is the concentration of the chem clean, because then it will tell us the concentration here. Okay, which is what we want, because from that concentration we can move down to find out what was that concentration here. Okay, because this concentration will tell us the concentration here. Yo, yani. So that is a backward calculation. So basically we're going to do this business here. So we're calculating things backward. We're doing a retrospective study if you're doing research. Starting at the end point, trying to trace it back to how it originated. Okay, all right, okay. Now let's deal with this one. There is the balanced equation, which you guys are spoiled, by the way, because you should be doing this yourselves. But anyway, it's fine. It says now calculate the mass of ammonia in 1 decimeter cubed of chem clean. Okay, 7 marks. So it's one of those questions that obviously are the harder ones. But if you're a chemistry student, you have been into my channel at least for some time, you should already be able to work out these things. Okay, already there's plenty of questions around this that are done on this platform by multiple good, presenters. So you must have found a way of getting around these questions. The key here is understanding what is given and what is its utility in giving what you need. Okay, let's move. So we're going to start. We want the concentration of our ammonia, basically. So since this is a complete titration, we can use our titration equation CA VA over CB VB equals NA over NB. Okay, yes, when everything gets taken to the end point, this becomes our means to an end. So now what is the concentration of the acid? Is 0.10 into, what was the volume of the acid that we used is 18.7. Now divide by, now the concentration of the base is what we want, but the volume that we used is 22 of the bigger one. Okay, all right, okay. Now this is a 1-to-1 ratio, so it's just going to be 1/1. Okay, again we do our favorite gymnastic of cross multiplication, which is very versatile indeed. This will tell us that indeed our concentration of base is going to be 0.10 into 18.7. These volumes you don't need to convert because they are in a ratio, so we can actually sort them out just right. So therefore the concentration of our ammonia there in that 250 centimeter cubed is this one, 0.10 into 18.7, then divide by 22, gives us a 0.085 mole per decimeter cubed. Okay, so that means this one is essentially 0.085 because we just took a smaller volume of the same concentration. It's like when you pour a cup from a bottle of Coke. Okay, so that cup has the same concentration as in the bottle. So now that we understand, we now want to say what was the original concentration of that 20 centimeter cubed. But what we know is that the number of moles contained here of ammonia, we know that, well, the number of moles didn't change because we used the same. So we know that the number of moles of NH3 is going to be the same as the number of moles of NH3 there as well, because that is the same amount that we used. We just added water, that's all. So all we know, we can say, but well, we know that N1, or we can say the initial is equal to the final, okay? The initial number of moles equals the final number of moles. This implies that now the concentration that was there initially multiplied by the volume that was there initially is going to be equal to the concentration that we ended up with multiplied by the volume that we ended up with, because CV defines number of moles. Okay, all right, okay. Now let's move. We substitute. So the initial one was 20 into, okay, let's just start it like this because we want the concentration. So we know that concentration into 20 is going to be equal to, we found out this is 0.085 into, now this is 250. We use the big one. We don't need to change these ones. Therefore, the initial concentration is going to be 0.085 times 250. Ixesha liyabaleka. Over 20, okay? Great. Therefore, the concentration, the initial concentration of our ammonia is going to be that one. So maybe let's not write this one like that. Let's just say the concentration, the initial concentration. We put that I as a subscript. Yes. So this is going to be 0.085 into 250 divide by 20. I'm getting a 1.0625 mole per decimeter cubed. Okay, so that means this 20 centimeter cube that we poured here was of this concentration. Now you can see this is per decimeter cubed. That means in 1 decimeter cubed we have how many moles? We've got that moles. So we can say, therefore, the number of moles of ammonia right in 1 dm cubed is going to be 1.0625 moles. Right, that is the most important thing. You get me. And then what is the story? Now we can work out the mass. We can say this implies that now number of moles equals mass over molar mass, which implies that now the number of moles is 1.0625 equals the mass that we want. The molar mass of ammonia is going to be 14 plus 3, which is essentially 17. We can say, therefore, the mass of ammonia in 1 decimeter cubed is going to be equal to 0 up. It's 1.0625 into 17. Ziyabuya 1.0625 into 17. So this gives us 18.06 grams. Okay, that is quite a lot of ammonia there. So that is it, guys. So you see a bit of logic when you got to this stage. Logic had to come in, because if you don't use it, you are going to be dead. So do you see, guys, all of the stuff that we can imagine in our minds when we're thinking, sitting there, if I was to think of this exam, what preparations mentally could I do to put myself in a state of preparedness or readiness and to make sure I maximize on what I get, it works. So you can see that all the stuff that we did, you see this one is a long one. It's a long, lengthy calculation. It's even longer than the KC for just 7 marks. Anyway, what is important here in physics, because it's a sub question where we used this formula, we're not going to give you a mark for that, but we can give you a mark for this substitution and this answer. It's important, okay? Secondly, determining this concentration is a mark, okay? Of course, I was not supposed to put this thing there. I was just talking at that time. So we've got our 3 marks. And to also know that this is the number of moles, that is the 4th mark. And essentially calculating the molar mass there, that is our 5th mark. And doing the things there, that is our 6th mark. So where do we give our 7th mark? I'm trying to think. So technically, this formula becomes a bit strange. So isn't it? You can get it here or you can get it there. It doesn't matter. That is where the 7 marks could be arrived at. Okay, so let's do the last question. 7.2.4. Now the question says, will the pH of the solution at the end of the titration be greater than, equal to, or less than 7? Obviously, we know that here we are reacting a strong base, a strong acid, and a weak base. Now this one is going to be an acidic salt, because ammonium chloride is a salt, right? It's going to be an acidic salt. So the resulting pH should be less than 7. Do you see our mental preparation really doing things for us? Less than, yeah, they said less than 7. Now it says write down the relevant equation as a motivation for the answer. Of course, we know that when you take NH3, no, this one is from the products now. So we know that NH4 plus aqueous can protolyze the water in the solution. It will protolyze this guy to form an oxonium ion plus the ammonia, which is a weak base. So this is an acid. It's a strong acid, and because of that, dude, that is the reason. So obviously we're getting a mark there and then 2 marks for that one. So we scoop the 21 marks and we smile on. Let's do another question. So you see, guys, if you pace yourself so well and you have the knowledge, you can really dig a hole in these exams, a huge one, and you will come out with a big chunk of gold and you will be a wealthy man, meaning you're going to get your distinctions. Anyway, electrochemistry. This one is easy. What do you need for electrochemistry? Well, yeah, just understand what is an oxidizing agent and what is a reducing agent, because this is very important. Usually oxidizing agents are ions, okay? Just remember that. And then remember, reducing agents are usually solids. But it's not always the case, okay? Usually. That is the usual story, okay? So, of course, here you need to know to calculate the E cell. Okay, so that is most important. Again, basic stoichiometry. You can be hit with that here. Okay, usually this is what creates a bit of difficulty in these solutions. And then, of course, Le Chatelier's principle. Applies here. And then the last thing, please know table 4a. That is your absolution, okay, and the periodic table in general. Okay, these are some of the things you just may want to think about and make sure you are clear. Okay, let's go on. Now, learners want to identify an unknown metal X using a standard half cell. They set up an electrochemical cell under standard conditions, which you already know, using 2 half cells, okay, as shown below. Okay, I think there was a bit of a mess in this one. This was supposed to be stuff like this, so it didn't copy so well. I went and then the other one isn't shining. iPhone. I went. Now, so snacks lab. Okay. Now that's what we've got. So we don't know what is what at this point. Now we're told the initial EMF of the cell is this. But what do you know? We know that the E cell of the hydrogen is 0. So obviously this thing belongs to whatever is that electrode. Okay. Now state the standard conditions, easy marks. So we know that the concentration is equal to 1 mole per decimeter cubed. Temperature is 25 degrees Celsius or 298 kelvins. Then if gases are involved, which are in this case hydrogen gas, should be 1 atmospheric pressure. Okay, I forgot the actual number in pascals, but that one in pascals. I think it's 1,00 something pascals, whatever. Anyway, we move on. Or is it 100 kilopascals, something like that? Let's move on. So those are the 3 marks. Of course, you look at the marks, you will gauge how much you are supposed to sink. And then it says state one function of component Y. That is the salt bridge, right? So this one completes the circuit. Okay? Or facilitates. So this one facilitates ionic movements to neutralize the solutions. So you can pick any one of the 2. That is important. Now 8.3, it says identify X by suitable calculation. So we know that every time that question is popped, we are to use our formula By the way, we still need something. It says now after the cell is operated for some time, it is found that the mass of electrode X has increased. So if electrode X has an increase in mass, this means this is the cathode. The cathode in a galvanic cell always increases in mass, and that means this is the oxidizing agent. Okay, great. So this implies that 1,20 is equal to, this one is this E cell of X, and the X here is plus, right? Is the positive ion. They said it's a 2 plus, okay? Minus, this one is 0, by the way, so there's nothing. So essentially, we know that the E cell of those 2 plus ions is 1,20 volts. Then we go and look for it using table 4a. And then we will see that, okay, there the plus 1 comma don't, so there it is. It is platinum. So always double check that there are no repeats, okay? So far it looks set that we can say therefore element X is platinum. In fact, they said electrode, didn't they say? Identify X, yeah. X is the electrode, so we can say therefore X is platinum. Great, we have identified it. Or you can even write the formula, but they said name. When they say identify, you can write formula or name, because it didn't specify exactly what must you say and what must you not say. So 5 marks, I want. Formula, of course, identifying the hydrogen one and the general substitution, and essentially working this one out eventually. That is 4 marks, and then the identification 5 marks. Okay, makes a bit of sense. 8.4. Write down the oxidation half reaction that takes place in this cell. Obviously, it's only hydrogen that gets oxidized. So hydrogen gas gets oxidized into 2H plus ions plus 2 electrons, right? But you can go back and check it. There is the guy that we're talking about. So we are sorted. We can see it. It's there. And we wrote it properly. So don't do double arrows. You're going to be dead. Okay, it's in one direction from right to left. That's oxidation in table 4A. So how many marks were we scoring there? The marks that we were scoring there is just 2 marks. So you see, copying things, you're getting 2 marks. That's wonderful. 8.5 says, okay, half cell, this one, the platinum one, is now replaced by the gold one, okay? Now it says the initial EMF of this cell is now. So knowing that hydrogen is 0, this is obviously the electrode potential of gold. Now as the cell operates, now the gold electrode increases in mass, obviously it's a cathode. Now arrange the oxidizing agents X, the platinum ions, the gold ions, and hydrogen ions in order of increasing strength. We know, of course, that hydrogen is a lower one. So H plus ions are of low oxidizing ability compared to the platinum one, which is 2 plus, compared to gold, because this one gives us a higher voltage. So it's going to be the gold. Okay, we did that. And then it says, fully explain the answer. Well, we know that gold okay, we can just say H plus ions are weaker oxidizing agents than platinum 2 plus ions, which, okay, let's start here. Hydrogen plus ions have the electrode potential of 0 volts compared to platinum 2 plus ions of 1,20 volts, which is also lower than the gold ions, 3 plus ions of 1,5 volts. All right, that is important. We can say therefore hydrogen plus ions are weaker oxidizing agents than platinum 2 plus ions, which also are weaker than the gold ions. All right, so that is it. We are sorted, because they needed us to talk about the strength. So the strength is all about the oxidizing ability. You see, our mental preparation talking about ions being oxidizing agents than the solid forms. Right. So guys, I'm telling you, man. So you can get a mark for that order, get a mark for stating their electrode potentials and talking about their oxidizing ability. It looks like correct to me that the 3 marks are what we're getting. So let's quickly take down question 9. So question 9 is the electrolytic cell. So similar thing as the electrochemical cell. The only thing is that this one is a non-spontaneous. It uses power. So that's just the only difference. Otherwise, the rest is just history. Now, the simplified electrolytic cell below is used to electroplate a metal spring. So if we're trying to plate this one, then it means this one is the cathode. Okay? And if it is the cathode, it is the negative terminal. So that means of our power supply, the shorter one is on this side. So that is the negative terminal, that is the positive terminal. This tells us then that this is the anode. Okay? And this is now the positive terminal. Okay. And then in the cathode, we still undergo reduction. This one will still undergo oxidation. Okay, great. Now we are sorted. Then we are told here, zinc nitrate solution is used as an electrolyte and R is an electrode, okay, which they don't say much about. Now it says define the term electrolytic cell. Again, easy marks. Definitions is the pap and place of the physical science. Okay. An electric is a cell where electrical potential energy is converted to chemical potential energy. Or we can say it is a cell which uses electrical energy to drive a chemical reaction. There's plenty of ways you can phrase this depending on how best you understand it. Again, stay away from cramming. Try to make sure you understand these things enough to just find it easy to go into definitions without trying to memorize and try to remember word for word. This is what blocks your minds, guys. This is what scares you off. And this is how you end up losing unnecessary marks. So please, man, pay attention to detail. That is the best thing I can tell you. Pay attention to detail. Take nothing for granted. You will succeed in the sciences because then your logic has a substrate to play around. But if you don't possess knowledge that is detailed, where will your logic come in and work? It will always try to look for things that are distant, and that's how you lose it. And that's when you start saying this thing is difficult, and yet it's nothing, guys. Please stop saying that thing that physical science is difficult. It's challenging, yeah, somewhere, somehow it will. But isn't it life challenging in general? It does challenge us all. Otherwise, why are there people who get depressed? Why are there people who get anxious? Why are there people who are just hurt? Why are there people who are challenged to a point where, you see poor versus rich? The rich ones are not really blessed. They work hard, they take on challenges and they do not shy away from those. Win or lose, they go for it. And that's why when they win big, okay? Sometimes they lose, but you don't see it because of their motivation. So please, man, just do yourself a favor. Just get used to the way life is and know that it's a constant challenge. So don't shy away from challenging aspects of life. These are man-made after all. So why not challenge back? Anyway, let's finish up here, guys. I will talk nonsense now. Which electrode R or metal spring is the anode? The anode is going to be electrode R, right? Yes. Give a reason for your answer. Well. It is connected to the positive terminal of the battery. Okay. You can just say the anode is the positive terminal of the cell. Whatever. Battery, cell, whatever. All we know is that if we're electroplating the spring, it definitely has to be the cathode, and that one becomes the positive terminal. Again, it's one of those questions where you see the answer is pretty vague, you know? So you just think, yeah, man, whatever. I just say whatever is best, and it should work. So that's it. 9.3. Says now write down, so easy stuff. So these questions are usually easy. The equation for the half reaction occurring at the metal spring, okay? Obviously, this one will make this one negatively charged. This one will become positively charged. And then, of course, when we pass a current through our electrolyte, remember zinc is in ionic form, so we've got zinc 2+ ions there. And in this solution, we also have the nitrate ions. These ones are 1-, okay? So, obviously, a positive ion is going to latch onto the positive terminal, the negative terminal. Opposites attract, and the same thing. But now the question is that, will the nitrate ion be attracted there? Yes, because it's negative, but there will be no reaction. That ion, it's a compound ion. It's pretty stubborn, okay? If you look at your electrode potentials, you'll see that there is nothing that can oxidize the nitrate ion, okay? We can only use it as a form of, we can reduce it, yes, but we can't oxidize it. So that is the story. So now what are we saying? The equation that is happening at the metal spring is going to be reduction. So essentially it's going to be zinc 2+ ions plus 2 electrons to form zinc. Okay, which is a solid. You can add those states of division, but they are not necessary, so you get your mark. Please, your arrow must be a single arrow, or else you're going to be dead. And yes, you write it the way it appears on the table 4A, or else if this is on the right hand side, you lose marks. Okay, all right, okay, so we're almost there, guys, so don't be in a hurry. Just take your time and get things done, okay? 9.3.2, it says name or formula of a suitable metal that can be used as electrode R. Well, I would choose zinc, okay? Since I am going to actually be forming these ions of zinc, because if I want to electroplate this, remember, as many zinc ions latch onto this, if I don't replace them, then I will not have enough to plate this properly. So I will need the same one as in that solution, usually. But of course, you can do other things, but what is important is the fact that we need zinc ions here, because we're already attaching them there, so we need to supply them. As we take them out, this one must be releasing them. So that is the story. And then it says at 9.4, explain the answer to that question. Well, we'll say that it will provide the zinc ions needed. And what else? So it will provide the ions needed to electroplate the spring. Again, what else? I don't know. What is the other one? Because they're giving us 2 marks. But they just said explain the answer. I mean, that should be all right. That is enough for 2 marks, is it not? Is there anything more? The one thing that we should know is that zinc nitrate is soluble as well. Ayman. Is soluble in water and therefore will not form precipitate. So we don't want a metal that is going to come in here and take those nitrate ions and form a precipitate, and then we end up without a metal coming up there. Instead we start, reducing water into hydrogen gas, things like that. So yeah, essentially we want something that is going to form a soluble solution with nitrate so that we can be able to remove those ions back into our electroplating. So perhaps those 2 are enough, or even just 1 is enough. Alright guys, this is the end of our attempt to give you a bit of a mental preparation for chemistry exam, at the same time solving this so that you can see exactly the utility of some of the things that you can think about and try to make sure you maximize on them in terms of knowledge and experience through practicing, and eventually you should not find any difficulty dealing with these questions. Otherwise guys, goodbye from me. I will see you next time, if there will ever be a next time. By the way, the physics paper I have that I downloaded from Stanmore Physics, and as well as essay exam papers, is incomplete. It's missing the MCQs, so I will not be able to do that thing. But if you be watching here, like my good friends, Mr. Katleho, or I don't know, Katleho is a unisex name, so it could be a lady, it could be a guy, I'm not too sure. But Katleho gave me the maths paper to complete paper. And Mr. Dooley also attempted to give me the papers. Unfortunately, he had the same as myself. So yeah, if you guys have the paper that is full for physics paper 1, please do forward it so that I can do it all as well and give you some of the pearls that you may need to kind of get your mind into the groove, because now your trials are coming soon and it's going to hurt if you don't know your work. You don't want a steep hill towards your finals. All right. Goodbye. See you next time.